Alright, we're going to begin section 14.2 in this video, which is double integrals in polar coordinates. Alright, so first we're just going to go back and look at what we know from trigonometry. So from trigonometry, we know, so if we have some right triangle, it makes an angle theta with the positive x-axis. This length is x, this length is y. This will be our radius. And we have the relationship cosine of theta equals x over r. Sine of theta equals y over r. And x squared plus y squared equals r squared. So from that, we get the following relationship. Between the polar coordinates r comma theta and the rectangular coordinates x comma y. So we have x equals r cosine theta, y equals r sine theta, and x squared plus y squared equals r squared. So now we can go back and forth between polar coordinates and rectangular coordinates. So what we want to do is we want to evaluate integrals using polar coordinates, because oftentimes a lot of integrals are easier to evaluate in polar coordinates excuse me, versus rectangular coordinates. So let r be equal to the set of points r comma theta such that theta is between alpha and beta, and r is between two functions h sub 1 of theta and h sub 2 of theta. So now this is what our regions, how we write our regions in terms of polar coordinates. We have theta is between some constant, and r is between a function of theta and a function of theta. Now that we won't encounter where we switch. I actually can't think of any instance, but we'll see when we go through some examples and we encounter anywhere we'll switch that r is going from constant to constant and theta is going from, actually I know we won't encounter any. So we're not going to encounter where r is going from constant to constant and theta is going from function to function. It'll always be theta is going from constant to constant and r is going from function to function. Now, of course, function to function could be constant and constant as well. So they could both be going between constants. All right. If f is continuous, on R, h1 of theta is greater than or equal to 0, and 0, or beta minus alpha, is greater than or equal to 0 and less than or equal to 2 pi. Then the double integral over R of f of xy dA equals the iterated integral. So still our constants always go on the outside. So it's going to be from alpha to beta on the outside. Our functions go on the inside integral. So h1 of theta to h2 of theta. Now, their function was f of xy was written in rectangular coordinates, but we're switching to polar coordinates. So we've, if our bounds are in terms of r and theta, we shouldn't have x's and y's in here. So our x is going to switch. So f of our x is now r cosine theta, and our y is r sine theta. And now our integrand is going to have another aspect to it. There's always going to be an r in there. So these are r's. So then that's dr, and these are thetas. That's d theta. When you switch to polar coordinates, don't forget to, in your integrand, include that r right there. All right, so you're going to have to insert that in there whenever you switch to polar coordinates. All right, so now let's look at an example. We'll do number 6 in your textbook on page 921. So page 921. Number 6 says, in exercises 1 through 6, express the integral as an iterated integral in polar coordinates and then evaluate it. And they give us the double integral over r of x squared dA, where r is the region bounded by the circle r equals 4 sine theta. All right, so the double integral over r of x squared dA. And they said r is the region bounded by the circle r equals 4 sine theta. So that's all they give us. Now, let me write that here. Now, the same thing applies in this section as applied in the previous section, that we always want to sketch the region over which we're integrating. So you may remember from Calculus 2, I think is where you all learn how to sketch regions like that, or what things like that look like. I don't think I learned that in Calculus 2 when I was in school, so I'm just going to go through and show you all how to do it using the relationship between polar and rectangular coordinates, because we're familiar with things in rectangular coordinates. So I'll just switch this to rectangular and we'll sketch it that way. So r is the same as the square root of x squared plus y squared. That's just from our relationship that we had previously between rectangular and polar coordinates, equals 4 times sine of theta is y over r. So that's going to be y over r. But remember, r is the square root of x squared plus y squared. So now we have everything in turn. I mean, it doesn't look like it, but it's in a more familiar realm because we have rectangular coordinates. Everything's in terms of x and y. We don't have any r's and theta swimming around in there anymore. So if we multiply both sides by x squared plus y squared, the square root of x squared plus y squared, excuse me. All right, we get this. And we want to figure out what does this look like so we can actually sketch our region. So let's move everything over to the left. We get x squared plus y squared minus 4y equals 0. And now we're going to complete the square on these y terms. We'll get x squared plus y squared minus 4y, and we take half of this, which is negative 2. We square it and add it to both sides. So negative 2 squared is 4, so we add a 4 right there, which means we have to add a 4 over there as well. So now we get this as x squared plus y, whatever half of that was, just 2, or negative 2, excuse me, squared equals 4. And now we can see, remember this is a planar region. We're not talking about something in 3 dimensions right now. They just told us the region R. So this is something in the XY plane. So this is just going to be a circle. So this is a circle with radius 2 and center 0, 2. All right, so now we can sketch our region. In the XY plane, and we sketch that, our center was 0, 2, and our radius is 2. So we're going to get a circle that looks like that, and that's our region R. All right. Now we're not doing type 1 and type 2 because we're doing this in polar coordinates. So we just need to figure out what do R and theta vary in between. So let's just we'll start with R. So right here, R is equal to 0. And R is always, you're going to come from the origin. It's going to be the distance out to your curve. Right here, R is equal to 0. And then we'll have some radius right there. And some different radius right there. Another radius right there. And another radius right there. So if you notice, it depends on what angle theta we're at. So R is a function of theta. So right here, for instance, from there to there, that distance is 4. So when theta equals pi over 2, our radius is 4. So first, let's just figure, so now we talked about R. So R equals 0 is the smallest value we're going to get. R is always going to be greater than or equal to 0 because it's a radius. So we see that R is greater than or equal to 0. Now we could go through and try to figure out what this is, but we already know what it is. It's that right there. So, and we see that that makes sense from our discussion of R, that it varies, the radius varies with theta. The smallest it is 0, and it goes out to here, because remember, we want this entire region. So R is not fixed at this. That would just be this circle. And nor is R fixed at 0. That would just be this point. R varies at every value between 0 and that. So R goes between there and there. Now, what does theta vary between? So be careful not to think that, okay, I have a full circle. That means theta goes from 0 to 2 pi. Now, if this circle were centered at the origin, that is the case. But theta is the angle we make with the positive x-axis. So we never, like, if you say, okay, 0 to 2 pi, that means eventually we're down here. But we really don't need to go down here to 3 pi over 2 ever. So a couple of things you can look at is, okay, well, this is clearly theta equals 0. That's clearly theta equals pi over 2. That's clearly theta equals pi. But you can also pay attention to the function that you're considering. We need our radius to always be greater than or equal to 0. And our radius is in terms of sine right here. And sine is always greater than or equal to 0 between 0 and pi. All right, so our theta will go from 0 to pi, and you can check and make sure, or not, you can kind of check some values to make sure that, okay, when whatever theta is equal to pi over 4, do I end up getting at this point right here? When theta is equal to pi over 2, do I get 4? So if theta is equal to pi over 2, do you get your that your radius is 4? And yes, you will. When theta is pi, do you get your radius is 0? And if you put theta is equal to pi right there, you are going to get your radius of 0. So your theta is coming all the way around, and you're getting that entire circle. All right, so now what we have is our region R equals the set of points R theta, such that theta is going between 0 and pi, and R is going between 0 and 4 sine theta. So now we go back to our original integral, and we need to set that up. We need to make an iterated integral, and make sure we don't forget to change our integrand, and we don't forget to add that R to our integrand that is present when you're doing an integral. You're integrating in polar coordinates. All right, so now we had that the double integral over R of x squared dA is equal to the iterated integral 0 to pi and then 0 to 4 sine theta. Remember, your functions always have to go on the inside. Now x squared, but x in polar coordinates is r cosine theta, so it's really going to be r squared cosine squared of theta. And then don't forget about your r, and then these are r, so dr, and these are thetas, d theta. Now for sake of time, I'm not going to integrate this yet because it's going to take a couple of trig identities. It's not the easiest integral in the world to evaluate. So what I'll do is at the very end of this lecture, if time permits, I'll go back and integrate this, but I want to do a few more examples before we spend our time on the actual integration. Setup right now is the most important thing for us. So I'm going to stop this video here, and then I'll continue with some more section 14.2 examples in the next video.